Well, thank you for joining us at Big Ideas at Microscale. Today, I have the distinct honor of presenting two really outstanding individuals in the field of 3D printing at the Microscale, Greg Nordin and Adam Woolley from BYU University. My name is Henry Patel, and I'm joined by my co-host, Robin. Hi there, Robin.
Hi, Amdeep, and hello, Greg and Adam.
Hello.
Hello.
All right. So I guess I'm going to give you a bit of my history with the two of you, with Greg and Adam, and I think it. I want to highlight some of the very key important things that they've done and why I think that they're going to be very impressive speakers during this podcast. I've had the chance of talking to Greg and Adam over the last year a couple of times, and every time that we spoke, it has always been eye-opening. The topic of conversation is always there's always a learning moment. There has never been a moment where we walked away where left head scratching. It's almost jaw open, just going, "Wow, I cannot believe that is really where the ideas can go and can take you." And when it comes to Greg, I had an encounter with him even prior to that when we met up at a conference in San Diego, and that again, an amazing gentleman at that time. It was very thoughtful when he came over and he introduced himself. And then prior to that, I saw him on this TED Talk in 2018, and that was for us. It was truly a starting point of just really understanding where technology was and where there was an actual vision of where it could be. And at that time, Greg sort of put a milestone and put down a flag and said, "This is where 3D printing should be when it comes to microfluidics." And so I think that that's probably what I hope we'll be able to sort of explore with them during this podcast. So, Robin, take it away.
All right.
Yeah.
Well, thanks, Tammy, for giving us the background and your relationship with Adam and Greg. I, for one, have only had one conversation just before this podcast where I sat down with Greg and Adam, kind of learned from them what they do. And since then, I've read a couple of your papers. And I must say, as someone who is still relatively new to the microfluidic field, and I've kind of been learning as I go, your papers are so well written and in general are very like simplified for someone who with limited knowledge, where I could actually comprehend a lot of what is going on, more so on the 3D printing side as opposed to the bioanalysis analysis and that sort of thing. But it's, I think for me, what I'm kind of looking forward to is kind of to pick your both of your brains and figure out kind of how you came across some terminology and just overall the concepts that you kind of developed regards to 3D printing. So let's get started and let's talk a bit about like both of your backgrounds, your professional backgrounds, your field of study, how you guys met, and how long you guys have been working together.
Okay, so my background, I'm in an electrical engineering department, but my bachelor's and master's are both physics. And I had intended to do a physics PhD, but found that when I was on that path, that my area of interest, which was astronomy and astrophysics, cosmology, I just didn't see how I was going to be able to feed my family. So I needed a plan B. And that meant going across town to University of Southern California to electrical engineering, where they had this fantastic optics and photonics program. And so I swallowed my pride, I thought, and moved away from physics to double E. And that was the best academic decision I ever made. So I come from kind of a different background, but I just love all things technical, and working with Adam has just been awesome. It's been a lot of fun.
Yeah. Thanks. And my background, I'm a chemist by training. Did my undergrad and actually my PhD in chemistry at University of California, Berkeley. So another good California school, Craig. Um, and
Yeah.
and then after postdoctoral work, I've been at BYU since 2000. I'm in the Department of Chemistry and Biochemistry, but research interests in microfluidics. I should say some of my initial research as a graduate student, we were developing microfluidic devices as part of the Human Genome Project, and so that was, a very early taste of what the power of microfluidics and also some of the challenges associated with using microfluidics. And Greg and I met. I think I met Greg was at University of Alabama, and then he interviewed to become a faculty member at BYU. And I think I met him at the interview because they said, "Hey, he's interested in microfluidics. You do microfluidics, and we're in different departments in different colleges." But I went there and I thought, "Wow, he's doing some really cool stuff." And the interesting thing is the projects that we initially collaborated on had nothing to do with 3D printing. This was, Greg, you can talk about it more, but it's about micro cantilevers and sensing. So anyway, it's interesting that we started collaborating on some things that we have completely left behind, and now it's we're definitely all in for 3D printing.
If we were to date stamp that, when would that have been?
Yeah, I don't know, Greg. When did you interview at BYU?
So that was 2005 when I interviewed and came to BYU, and then we
Oh,
started collaborating within a year or two of that.
Yeah,
oh wow.
it's been almost 20 years.
Prior to coming to BYU, my research was all focused on microphotonics, diffractive optical elements, micro and nanofabricated devices, MEMS, biosensors. And when I came to BYU, I brought all of that with my PhD students with me, and that's what we continued to do. And long story short, ended up moving more into microfluidics, and then had some the usual clean room issues with making microfluidic devices where, yes, you can do it, but it just takes a long time to do. And so, long story short, there started getting interested in 3D printing as a possible avenue for fabrication. And that's kind of how everything started with the 3D printing.
And did BOIU already have 3D printers in place, or was that like a technology you just
No,
happened to come across and you're like, hey, we need this in our lab?
no, I was one of the heavy clean room users here at BYU, and in fall of 2012, as I was looking at alternatives, kind of the hype cycle had started up on 3D printing with some of the original patents becoming out of date, and people being able to start doing things. And so I looked at that and thought, I wonder what sort of opportunity we could have here with microfluidics. And so January of 2013, I started a 5 or 6 senior student senior design project for a semester, looking at, hey, let's build a 3D printer. And so we took the scanned laser approach and we built something and started to photopolymerize things, and with the goal of microfluidics as the application. But by the end of the semester, it was obvious that that was not the way to go. We needed a different path. And so the DLP, or image projection type of stereolithography, became much more attractive after having gone down that dead end.
And we did buy some commercial 3D printers of various types. I bought an early version, one of the inexpensive FDM 3D printers that puts out a heated filament and patterns that. And then Greg and I got one of the early SLA dynamic light projection 3D printers that was commercially available, and it was nice to be able to make things, but just not at the microfluidic scale.
Yeah, we did a lot of early work with using several different commercial 3D printers and looking at commercial resins for microfluidics, and found that the resolution for the negative features, which are the key thing in microfluidics, just was not there. So we thought, well, gee, let's do our own custom resins, and maybe that will be good enough. And so we explored that, and we found that no, that's not good enough. You can get down to, I think the best we did was 60 micron tall channels by little over 100 microns wide, and that just wasn't the size scale that we wanted to be at, and it was difficult to get that to turn out well.
Sorry, this was for the commercial resins or your custom resin?
Custom resin with commercial
Okay.
3D printer.
Okay.
Yeah.
And so at that point, it was either, well, we just live with it, or we jump in and make our own 3D printers as well as our own materials and solve the real problems to get down to the size scales we need to be. And that wasn't necessarily an attractive proposition, but on the other hand, just living with what was available was also not attractive. So just decided to go for it.
Yeah, some of the projects we were working on using conventional cleanroom technologies, we were making devices in several different materials and aligning and stacking together 5 or 6 different layers. And I had a postdoc in my lab at the time who was just really trying to solve this problem. And the problem was that he would spend 6.5 days of the week
Wow.
working in the clean room trying to make devices for every half day that he could actually test devices. And it was frustrating that the yields and the abilities of the conventional clean room systems, especially as we went to very complicated fluidic structures with multiple materials and multiple layers, that it was just, we were not making very good progress. And so that was part of the reason I was open to trying something that was very different, unexplored, and not commercially available, just because of the potential it had to really allow us to make devices with the exact features we want in 3D space and with resolution that's appropriate for doing microfluidic experiments.
So now, when you were starting to develop the material and the platform, was there any other teams within the United States or anywhere globally that were also trying to find a solution to some of these things that you've described, Adam?
There are a lot of people trying different approaches. I mean, I think the most common one is I'm going to use commercial 3D printers and see how good they can get. And we had also tried that approach, and the challenge was it just, we could not make things small enough to do some of the experiments at the volume scales and with applied voltages and other things that we used to do that. So, I mean, there were groups trying to solve the microfluidic device fabrication challenges with 3D printing, but just the commercial options that were out there at the time wouldn't do it. I mean, they couldn't do it. And this was something we published sort of as a review, kind of a trends article about 8 years ago that pointed that out, that yes, 3D printing is great, but it only gets you, with the commercial systems, it only gets you so small. And to really address some of the fundamental challenges, you need a better system. And then fortunately, right around the time we published that was when Greg had a fantastic student who was able to solve a number of the key technical problems and make it so we could actually make the devices at the scale that we wanted.
And what were the sizes that you were looking to achieve? Like sub 100, was there a specific number that you have always been shooting for?
Well, sub 100 micron was the target, but even, I mean, if you're at 99 by 99 microns, there's still some challenges. We do in my lab, we do a lot of separation experiments using a technique called capillary electrophoresis, where you apply high voltages across a channel, and the larger the channel cross section, the more current that flows through, and therefore the more heating. And so, optimal sizes are in the 50 to 60 micron cross sections or smaller. And so that was the work that Greg's fantastic student, Hua Gong, was able to do, put us at where we could get down to about 20 by 20 microns. So, even under, maybe a suboptimal day, we were still able to print things that were well within the tolerances that we needed.
Yeah, that particular result, 20 by 20 microns, or 18 by 20 microns is what we published. That was done with our very first custom 3D printer with our own custom resin, and that involved a lot of detailed work to understand the kind of everything that goes into negative feature resolution. And so in a three-dimensional space, you have the XY plane, which is kind of the plane of the layers. And there, the key thing is what the projected pixel size is for these ultraviolet images that you project into the resin. Uh, and and that's kind of a straightforward thing. I mean, the smaller the pixels, the better the potential resolution you could have. But the one that is more difficult and that most people stumble on is the resolution in Z, which is orthogonal to the layers. And there, it's all about how deeply does the light penetrate the resin. And if you don't control that and minimize that, then there's no way you can get good Z resolution. And so that paper, together with the analysis in the 2015 paper that we did, um, really showed how you design your resin in conjunction with the 3D printer system to get high resolution in both X, Y, and Z. And so that Z dimension was really the crucial missing factor. Even though we did, I think, 7.6 micron pixels, which was much smaller than what others were doing, which was more like 27 microns in the best case, but usually more like 50 microns. And so our XY resolution was really excellent compared to what else was out there. But the real kicker was the Z resolution, being able to master that and get that to work out really well. And there, like I said, it's all about controlling the optical penetration depth. So that means in your resin, it's all about what UV absorber you put into the resin to limit the penetration of the light. And then the key factors there are that that absorber, its absorption spectrum, has to fully cover the emission spectrum of your source, which is typically an LED, either 405, 385, or 365 nanometer LED. And so choice of UV absorber is really what it boils down to with that Z resolution.
And so by the time that you got to, you had a solution, you're describing the actual solution that you came to. What were the stop starts that you had while you got there? Because that must have been far more an important learning experience of the actual stop starts getting to the actual final solution in this case.
Yeah, it's amusing. I mean, the paper that we published that showed that, I think that was the one, Greg, where Bryce went through 20 different UV absorbers. So we had a student who was just like, okay, here are some ones that match the optical properties we need, and then it's like, oh, but it doesn't dissolve in our resin, or it's fluorescent, and so we have this wonderful flow diagram that's in the paper that kind of went from this pool of 20 possibilities down to one that actually worked well for that initial paper. And we've since come up with a couple others that are suitable, in fact, better than that initial one that we identified. But that was certainly a part of it. Yeah, I don't know, Greg, what else?
Yeah, yeah. That choice of UV absorber was just crucial. And to begin, we started with Sudan 1 because we were using a 405 nanometer source. And the Sudan 1, while it's very effective, it's just this ugly orange color, and everything in the lab turns to orange because the students spill it, and I mean, it just gets everywhere. It's just nasty, and and so I just really wanted to get rid of that Sudan 1. I didn't want it in my lab anymore, and we shifted to 385 nanometers, where there was a greater variety of potential absorbers, and so this student that Adam mentioned was an undergraduate, Bryce Bickham, and he started attending our research group meetings, and he wanted something to do. And in one meeting, he piped up and said, "Yeah, what can I do? How can I help?" And I told him, "Well, in the basement of the library, there is this, I don't know, 20 volume set, each of them, 3 inches thick, that just compiles the absorption spectra of all these materials. Why don't you start pulling those out and just go through the absorption spectra, and here are the criteria we're looking for. This is the kind of absorption we want." And so he went through these volumes and just, page after page, and he would note down the ones that had an or an absorption spectrum that could potentially match what we were looking for. And so he developed this gigantic list of materials, and then we sorted through it for toxicity to get rid of the toxic ones. And in the end, we ended up with these 20 different candidates that we purchased, and we tried. And as Adam said, we had this set of criteria that they had to pass. First being soluble in the monomer we were using, and of course many of them were not soluble, so that got rid of them. And then there were other things having to do with measuring the absorption spectrum as a solubilized absorber in the resin, make sure everything was good there. And then there were other issues with different ones, like Adam mentioned. Some of them were fluorescent themselves, which kills your resolution, and then some of them also created polymer matrices that were just crumbly. They just didn't have the mechanical properties that were needed. And so in the end, out of these 20 candidates, one of them worked out really well. And so that's what we ran with for a number of years.
In one of your papers, you mentioned, like especially for the clear material, you mentioned that the yellowing of the device wasn't desirable. Did you find that to be a big issue when you were developing your custom resin?
I don't think that. I mean, the initial photo or the initial absorber that we identified actually has sort of a light yellow color to it, and that wasn't. I mean, it wasn't a showstopper for a lot of things. I mean, it was we had to kind of work around that the feature of the resin when we were doing fluorescence detection. So it was. I would say it was a challenge, but not insurmountable. And then, with the better UV absorber, the avobenzone, which by the way is just an ingredient in a lot of sunscreens, it's a good UV absorber because it's a good UV absorber. Anyway, it doesn't have the coloration, and I guess there's a little bit of something that happens post cure under certain conditions, but I think that's actually the photo initiator and not the UV absorber itself. So, yes, ideally, the less stuff that interferes with optical measurement in your device, the better. I mean, if you want to measure small quantities of things in a channel within a device, you don't want to lose your light to anything that absorbs. So, when we went to this better, clearer resin with the improved UV absorber, that's really the advantage. I mean, you could work with one that does have a tint to it. Obviously, going from the Sudan one to the NPS to avobenzone, we went from incredible amounts of light absorption to moderate amounts to essentially none. So that, at least in the finished device. So I think that was helpful.
It didn't really affect, I guess, the resolution or the final channel of negative void. What'd you call it? Negative void.
Yeah. No.
Yeah.
No. Yeah. It doesn't really affect the resolution. And also, just to be clear, the doing any sort of microscope observation of the 3D prints was always fantastic, because the final 3D printed surface was very flat and smooth, so you could look through it with a microscope, no problem. We always print on top of glass slides, so you could look through the glass slide and look in the other direction. And it's just perfectly clear and easy to observe the structures that you fabricate. And the only issue really is whether that tint and coloring affects whatever you're trying to do. In many cases, it doesn't. Okay. But as Adam said, we've shifted over to this avobenzone, so there really isn't much of a tint even. But in terms of microscope observation, that's never an issue. It's just always beautifully pristine.
Yeah.
Now, so this is the material side that you're sort of giving us a good sense of what that pathway looked like. What about on the printer side? What did you see from the commercially available machines, and what modifications did you guys start putting in place to end up to the machine that you had created yourself?
Well, I'm going to say a little bit first, but I mean, Greg's the one who really built it. But I would say this, when we went into this, and when I say we, it's primarily Greg and his students. It wasn't like, I wonder what the commercial system has. This was if we were to make this from the ground up, what would it be like? And I think the resulting features that are just completely radically different from commercial systems. I think one of the key features is we have the ability to control all aspects of the 3D printer. So if we want to shine a different amount of light in one pixel versus another, we can do that. If we want to do multiple exposures on the same layer, we can do that. And commercial 3D printers, that's something that has not, certainly at the time we started this was not something you could do. And so just having that ability to really, lift up the hood on the instrument and say, hey, I want to do this. Hey, we can do that. And I think that's the one of the key differences. And of course, Greg will speak to all the other things that went into the design.
Yeah, it's been a very long multi-year journey to get to where we're at. And just as kind of a teaser in terms of where we're at, I'm just going to hold up this little device here. This is a test device that we recently started using. It has 1,600 valves on it. Each valve is 150 microns in diameter. And this device right here that I'm holding in my hand, all of the valves work except for two. And those two we can trace back into defects of the film at the bottom of the resin tray. So we've gotten to the point where we can just do this incredible uniformity, repeatability, reliability, and there has been so much work that has gone into that. I mean, it's not like you can just come up with a design, turn on some 3D printer, plug in some material, hit a button, and voila,
Expect it to
this thing
work.
comes out perfectly.
Mhm.
That is not the story, even though that's where we're driving to.
Yeah.
And so, in with the very first 3D printer that we built ourselves, it was going back to, hey, I want some projection, an optical engine that projects the most pixels I can possibly get. And so with the TI micromirror array devices, that meant we had to go for a particular model, which of course was not the least expensive model out there. And so that was a 2560 by 1600 pixel or micromirror projection device. And then we wanted, very high resolution, so one-to-one imaging optics. And so we bought that optical engine with the optics from a vendor in Germany, and then we needed to do, all the build platform and its motion and the resin tray and how we're going to lift off from the bottom of the resin tray because we're building bottom up, and so we went with this uh, um, sort of OEM thing from a company in Taiwan, and so putting all of that together with our own custom software that controlled everything, that was our first shot at just seeing what can we do with this sort of a format, and that's where all of our early results came from, was from this. Just I mean, we took optical posts and beams and mounts and other things that we had lying around in the lab from previous optical projects and used that as the structure to kind of mount everything to, and created this ad hoc 3D printer. And because of the driver board in the OEM optical engine, we had to use a Microsoft Windows PC to drive the thing, which of course drove us crazy. And and with our version 2, which Hua, this PhD student of mine that Adam has mentioned, which he designed because, well, long story I won't go into, but at any rate, so he designed this version 2. And one of the things we desperately wanted to do was get away from Windows PCs, and so we figured out how to bypass some of the internal circuitry of this OEM optical engine and directly access the I2C interface, and just talk to all the hardware directly ourselves. And so that enabled us um, to get rid of the Windows PC, to put everything on or run it off of a little Raspberry Pi, so Linux-based system, and do all of the hardware control from the Raspberry Pi, and throw up a web interface so anyone could control the whole system just through a browser window. And that software has gone from that very first version, and we've refined it countless times over the years since, to where it's now very sophisticated and modular and pluggable, piece of software that runs all of our 3D printers of whatever configuration we've created. And so that's worked out really well. But as Adam said, because we write our own software, we do all of our own hardware, we interface to whatever sensors we want to use in our systems. That means we have complete control. So we can try any crazy idea any of us has, which is fantastic because we've tried a lot of crazy ideas. And at some point here, when we're ready to publicly or go public with what kind of the latest thing that we've done, I mean, people are going to look at us like we're crazy. But but that actually has led to this result of 1,600 valves that work, and it wasn't difficult to print that. So at any rate, that's just been a long haul with the software side. But the hardware side, there have been numerous generations of developments, and those have branched off into different directions to evaluate and try out, different ideas that we've had. But the long story short is now we're at what we call our HR 3.3 series of printers. HR meaning high resolution. The first three means this is the third generation of developed printers that we've done, and then the 0.3 is this is the third iteration of that third generation. And the reasoning behind this whole development process has been with version 1, yes, we got some great results out of that, and we learned a lot of really useful things. But we also found what the pain points were on the hardware and the software side and the process side. And so version 2 was an attempt to address some of those pain points and make it easier to and more consistently able to have successful prints. And then we learned more with that version 2, and then that initiated doing the version 3, trying to minimize some of the pain points that were still present, and likewise with the other iterations. And so now we're at a point where with this HR 3.3 series, we routinely train new students from freshmen to PhDs on how to 3D print, and they're able to be successful quite rapidly. Of course, the smaller you try to make your negative features, the more challenging it becomes. But the more skilled, the more experienced students who develop some significant skills, they're also able to have those turn out pretty routinely. So it's just been kind of a long haul there, but it's turned out just extremely well, I think.
And I just want to, just to circle back to the power of being able to control different things. I mentioned like, controlling individual pixels and different intensities, but there's also crazy parameters like who would have thought that the acceleration rate for moving your print away from the stage? We can even control that. And those things, those small things, just have an enormous impact on your ability to make high quality 3D prints. And so, you get a conventional 3D printer and it's like, this is the layer thickness you're going to do. You can control the exposure time for the entire print. And this is the resin you're going to use. And you're like, okay. And with us, there's just with the printers that Greg and his students have developed, we just have so much flexibility to fiddle around with the small things. And those are really the things that have allowed us to go from, kind of standard, with a commercial 3D printer, I can make channels that are about 200 by 200 microns on a good day, down to just some of the, this crazy stuff with, 1,600 valves in a single 3D print. So that's really it's just so powerful.
First of all, how'd you both not get so lost in changing out tweaking all these different little print settings and and in general, because you've developed the hardware, the printer hardware, the software, the resin, what would you say is kind of the most important to actually get good microfluidic devices? For example, is it really in the 3D printer? Is it in being able to change all these little details in the software? Or is it a combination of all three together?
So it really comes back to a couple of key ideas. And one is, what is the size of the smallest negative features you're trying to create in relation to the pixel size and the layer size? And the layer size, I just have to say, parenthetically, people think that the layer size is the Z resolution, the layer thickness, and that is absolutely false. The Z resolution is the optical penetration depth. And then once you know what the optical penetration depth is, or you've designed it, then you set your layer thickness accordingly. And that's discussed in our papers as to how you do that. But once you've got all that set, then it really comes down to are the negative features you're trying to create many, many pixels and many, many layers big? If they are, then it's not that big of a deal. You should be able to do it. But if they are relatively few pixels in size and relatively few layers in size, then that's where all the special sauce comes in, and that's where all the real finesse and the difficulties arise. And so over literally years now, we've just developed such a backlog of experience of how you deal with these things and how to think about these things and what additional knobs you need to turn and how you turn them, that we can get those things to turn out, pretty routinely. But if you approached things on that size scale, few pixels, few layers, and like you did the things that are many pixels, many layers, I mean, just you'll never be successful with it. And so this goes back to a set of ideas that we've tried to introduce where most people, in being familiar with 3D printing, think about, okay, we have this CAD design, so a design in virtual space, and we want to turn it into an actual physical embodiment of that design. And so 3D printing is you take this CAD design and you slice it up into these equal thickness layers, create one image for each layer, present each image sequentially in the 3D printer to your layer by layer resin setup that you're doing, and then expose each layer at the same for the same exposure time, and voila, now you've created your print. And that does work well for large features, large in terms of many pixels, many layers, as long as you have the other stuff right, like the optical penetration depth, etc. But when you go to high resolutions, a small number of pixels and layers, the game just totally changes, and you need additional flexibility. And so we published in 2021 in Nature Communications a paper that basically introduced a notion of a generalized 3D printing approach. And by generalized, what I mean is that for every Z position in your print, in your design, you can do the following. You can have a series of more than one image at that Z position. And you can polymerize different regions within the image area for different lengths of time. And you can do this by presenting different images that, maybe they overlap, maybe they don't, different exposure times for the different images. And so the bottom line is that within one Z position, one layer, you can have a wide variety of different optical doses that you've delivered on a pixel by pixel basis. And then instead of equal thicknesses, when you're trying to do these really high resolution things, often you need to mix that up and have different thicknesses for different, limited areas. And so with our generalized 3D printing approach, that's just no problem. I mean, you can do whatever you want in terms of Z positions and number of images, what the images look like, exposure times. It just gives you a much broader range of spatially distributed doses than the normal conventional 3D printing approach. So this generalized 3D printing approach is just really a crucial innovation in terms of being able to get these super high resolution negative features.
And I think one of the key things that, I have students who are non-engineers, undergraduate students who use the 3D printer and can turn those knobs. And part of the reason that they can do that so effectively to optimize 3D prints is that Greg and his students have done a really good job of connecting each of those parameters with some property of the resulting 3D print. So we know that if you change exposure time, layer thickness, step height, number of sequential images, all of these things we have a good understanding of what that does. And so that allows us to sort of logically and rationally choose which parameters to adjust. And we do have undergraduate students who are not engineers who can do that and create really nice 3D printed objects.
Well, one of one of the things that we would love to do is spread this knowledge to everyone. I mean, so anyone and everyone can do this kind of thing. We don't want it to be localized only here at BYU and things that we do with our collaborators. What we want is for everyone to be able to have this kind of 3D printing capability. And the unfortunate thing is in the commercial offerings, there just aren't printers that give you the flexibility to even see the knobs and know that they exist, let alone change them. And so one of the things we did early on, I think our first version of this was maybe 2017, 2018, probably 2018. We put up on GitHub and open sourced a print file specification that basically allows you in that specification to set all these different things on however fine detailed basis you want. You could make it so it just does normal 3D printing. That's easy. Or you could go in layer by layer, Z position by Z position, and tweak whatever you want. And so that's available up on GitHub. Anyone can use it. I think it's an MIT license. So, unfortunately, no other printer manufacturer has adopted something like that. We'd love to see them do it. We have evolved that spec. It's based upon a JSON file format, but we've evolved that spec to now it's really quite sophisticated. In fact, it's on my to-do list to have one of my students update to the latest spec that we use internally so that that's available externally.
Robin, you were about to say something?
Yeah, so I was gonna actually talk about, because you use the term negative features or negative space law. And when I'm going through a lot of literature, that terminology doesn't actually come up a lot. It's monolithic devices with closed channels. So I'm kind of very curious how you even came across that terminology in the first place. Did you hear it from somewhere else? Is that something you both developed on your own?
I don't recall hearing it from somewhere else, but positive features are kind of well known thing, and so with microfluidics, when you make a microfluidic device, of course, it's all about the material that's not there in the device because that's where the fluid is going to go. And so you're basically creating these negative features in some kind of a bulk material. And so rather than positive features that typical 3D printing focuses on, in microfluidics, the whole name of the game is these negative features. Channels. That's a void. That's a region in which there is no material surrounded by polymerized material, or a valve or a pump. It's the same thing. It's just the shape of what's not there is different. And so the 3D printing has to be tuned and focused on making those negative features so that you can have very small regions in which there is no polymerized material, because that's where ultimately you want the fluid to be.
Yeah, I mean, if you think about most conventional 3D print models, they'll show something like the Eiffel Tower or a boat or, a fly or a guitar or something like that. And I guess, the negative features, so the Eiffel Tower, the positive features are, of course, all the metal, and the negative features are the air. And we're interested in the air because that's where the fluid went. Once we've made this print, then we can fill that with liquids and we can control the flow, and we can use that to carry out biochemical assays and do some really powerful experiments.
And I guess the next there's also this big transition between macro printing and micro printing, and I think you guys have touched on the fact that even as you go down in scale, you now have to have that level of control in terms of pixel, in terms of your material. I'm wondering, Greg, in terms of your background in optics, what skill set did you have from there that you found valuable as you moved into microprinting and developing the printer that you had?
So for me, things that have been crucial are understanding the optical interaction with materials, which gets back to optical penetration depth. But when it comes to resolution in X, Y, as well as Z, it's just knowing how image formation works, knowing about diffraction, knowing about aberrations. And in designing an optical system, even though I don't design the lens system that we buy that goes with our optical engine, I know the details of how all that works, and I know what the specs mean in terms of the modulation transfer function, et cetera. And so just understanding in detail how the optics work has been really helpful for me just to understand on a micro scale what's going on. And in fact, I see in the literature all the time groups publishing papers where they model an individual pixel, its projection in the image plane, as a Gaussian beam. In fact, I just went through a paper 2 days ago that did this, and I've been seeing this for 15 years. And that's just absolute hogwash. That's not how it works. They are not Gaussian beams. And so it just drives me nuts. And we have a paper that we've been meaning to write for a number of years now that lays all this out and shows actual measurement results for what you really get in real life, which are not Gaussian beams at all. And we just haven't gotten to it. I mean, just haven't had the bandwidth to bring that to closure yet. But that's something we'll be doing one of these days, hopefully in the next year or so. It's on the roadmap for one of my PhD students now, so I think now it's actually going to get done. But at any rate, that optical understanding has been really helpful.
Yeah, can you just explain what is a Gaussian beam and what?
Sure. Yeah. So a Gaussian beam. So if you have a high quality laser pointer, the beam that it sends out is a Gaussian beam, meaning that if you project it on your hand and you look at that spot, if you were to take just a cut through there and plot the irradiance, meaning the power, that would follow a Gaussian shape. So it would be an e to the minus x squared over, whatever the parameter is for its width. And so Gaussian beams arise very naturally from laser cavity design. They are the zeroth order transverse mode that a laser cavity produces. And so most lasers, if it's a good laser, produces a Gaussian beam. And so for people in optics, you learn about Gaussian beams in the context of lasers because that's what they produce. And so you learn the properties of them and how you deal with them. And for whatever reason, I don't understand, people have taken this Gaussian beam notion and somehow transferred it over to image formation and image projection, and modeling each individual pixel as a little Gaussian beam, which is just absolutely wrong. And instead, it's the diffraction pattern of whatever your pixel size is, modified by whatever aberrations are introduced by the optical system. And ideally, your optical system is what's called diffraction limited, meaning that your resolution and fidelity is limited by actual diffraction of light, which you really can't get around. That's the best you can do. And so what happens is, in designing an optical system, you reduce all of the aberrations so that their impact is about the same as diffraction is. And then you don't do anything more than that because that's just wasting money, because it's not going to have any improvement because diffraction is the ultimate limit.
Amazing.
Your 1600 valves, was that created for a specific purpose, or were you really limit testing the abilities of the 3D printer?
So it doesn't have a functional purpose in terms of an end application. This is simply a test design to allow us to evaluate the effects of turning some of these knobs we've been talking about. So for example, we have a new uniformity correction method that we've developed, and so this design that's kind of uniformly placing these valves across the entire projected image area is something we're using to test the effectiveness of this uniformity correction. And the results are, yeah, it works great. And then there are a variety of other issues involved as well, that this also is a good just sort of test design to evaluate what happens as we change various things, and how effective it is in terms of getting a uniform result out.
And what other microfluidic features have you sort of experimented with? I suppose like droplet generators, regular channels.
Oh, you name it,
Yes.
we've probably experimented with it. And a bunch of things that are probably on no one's radar. So, for example, we have done things like 3D printed super hydrophobic surfaces out of hydrophilic materials. So you basically have this surface that's the native material is hydrophilic, but because of how we pattern it, it turns out to be super hydrophobic. So the contact angle for water is 140 degrees or more. We've done other things like created this little cone, little tiny thing. You can barely see it with your eye, and on the top of it, put this little ball, and then we have a channel that goes up through it. And because it's a hydrophilic material, if you wet the surrounding area, it draws liquid up through that cone, and it spills out over the ball and kind of uniformly coats the ball in a couple of microns thick of water. And then it flows down the side. And then as you get evaporative loss, it's self-replenishing. And so, why would anyone want a little tiny micro fountain like that? Well, it turns out we have another group that we're collaborating with where they're looking at whispering gallery mode lasers. And so you can take that thin water film and bring this tapered fiber up close to it and couple light into that water, and it's ends up being trapped and going around and around in that water through total internal reflection off the surface. And why would anyone want to do that? Well, they're looking at some different crazy laser ideas and materials issues and whatnot. But the point is, because we have this fabrication capability, we can make these kind of crazy shapes, and they're effective and they work well. Or with the same group, another thing that we did and published on is they have these small chips, maybe a square centimeter, with silicon photonic devices on it, ring resonators, Mach-Zehnder interferometers, whatever. And then you want to be able to control the refractive index in the optical paths. And so we've created 3D printed microfluidic devices with integrated gaskets that you can just compression attach to these silicon photonic chips. And then just by changing the salinity of the water, you can change the refractive index that the light sees in the waveguides and do a bunch of tuning. And it's almost a passive thing. It takes almost no energy to do that. And in the world where you need that sort of capability, the only other approach that's really been shown to be effective is to use heating, and that draws a lot of power. And so at any rate, just these off the wall kinds of things. So we've done tons of traditional microfluidic sorts of devices and components and integrations, but also kind of crazy, way out there sorts of things as well.
Yeah, I'd be happy. I mean, a few of the things that this is, the part that I care a lot about, because we use these things to do bioassays, to detect molecules and things that are related to diseases. So, I mean, we've created a combination of pumps and valves and chambers that allows us to collect certain types of molecules and concentrate them. And that can be based on, simple chemical interactions or affinity-based interactions, something like, DNA base pairing. We've also designed 3D printed devices that can create chemical gradients. So the concentration of a given chemical varies as a function of position within the device, and that can be useful to study things that happen to cells, how they respond to chemical cues. We've used the pumps, valves, and a diffusive mixing chamber to do serial dilution, which is a really common process in a biochemistry lab where you want to study the effect of a compound as a function of concentration. And so you have some poor student who does a bunch of pipetting to make different concentrations over several orders of magnitude range, and then you put them into some kind of a test system where you evaluate that. And with this combination of being able to create 3D printed pumps and valves and diffusive mixing, which only occurs at very small size scales, hence the need for truly microfluidic devices, we can bring in a concentrated solution and water and then flow those two together and in a controlled way create 10 different concentrations that go over a factor of about 1,000 range of concentration just by a designed flow system. And we can create that and have it creating stable outputs of the different fluids over the course of just like a minute to get it to stabilize. So, there are a lot of useful and interesting things that you can do with the microfluidic devices, and a lot of also off the wall things, and probably some things we haven't yet even thought about that we still need to come up with some crazy ideas to address.
So now, in terms of the material that you've been using to develop all these devices, is this just the exact same material that you've used right across all these unique platforms that you've developed?
We have one that's sort of a go-to that is the common denominator, and this is polyethylene glycol diacrylate, and that was chosen for a number of reasons. One of them being that my lab had used that previously and done some photopolymerization using sort of conventional cleanroom technologies to make devices. It's also a crosslinker, a combined monomer and crosslinker, because it has two reactive groups, and so that makes it useful as the polymerized material. And the fact that it has polyethylene glycol groups is also important because those that particular chemical group is known to, when it's formed into materials, it's known to resist non-specific adsorption of things like proteins. So if you want to do bioassays, you want your device material not to have stuff stick to it. And so we've, that particular base material. Now we are doing a lot of things now where we're substituting, minor components, but, a lot of, that particular resin has really been our go-to for that. But there's always exploration and trying some new add-ins, different materials. And we've innovated probably more in the UV absorber space, and also done some things with different photo initiators. But we do have, our standard go-to one that just always works. That if a student's coming in to try something, we recommend that one first.
Yeah, and we should also mention that these formulations for resins are all available in our papers. Anyone can pick up one of our papers and see what the components are and order them and mix them up and basically have the same materials to work with.
I remember in a previous conversation, when we first introduced the idea of doing the podcast, you mentioned some very interesting things that, like 3D printing in a vacuum, that I'm wondering if you both can talk a little bit more about that, because that concept alone sounds crazy to me. So what is it that you're trying to do there, and are you still pursuing this idea in the first place?
I can maybe give some initial background, and then I'll let Greg talk more in the details. But I think part of the rationale is that when you 3D print things, you use a polymerization reaction, and that's initiated by the light from your projector, the optical engine that you use. And there are a lot of things that inhibit polymerization. One of them is oxygen. And so, that's I think the initial thought experiment was, well, if we do it in a vacuum, there won't be any oxygen. Mm-hmm. And then it turns out if you do it in a vacuum, there will be other things that happen too.
Yeah. So the vacuum thing. Yeah, we're just putting together all the data to do a big paper to kind of reveal the whole thing. But the bottom line is this: when you 3D print at atmospheric pressure in a normal lab, the resin that you're photopolymerizing has some dissolved gas in it. One component of which is the oxygen, which actually serves a useful function as an inhibitor. And in our paper we'll go through all the details of why. But it turns out that dissolved gas also causes you problems, because when you are polymerizing against whatever the bottom of your resin tray is, let's say a Teflon-like or FEP film, that's what we typically use, then your polymerized material is attached and adhered to that film. And then when you go to do your next layer, you need to pull it off of the film and come up and then come back down to whatever your layer thickness is. And we often use 10 microns, although we do other things as well. But when you are pulling off, then you've got kind of this suction of you're creating space where resin needs to come in very rapidly. And so you're dramatically changing the pressure conditions locally within the resin. And it appears that what that causes is for some of that dissolved gas to come out of its dissolved state into a gas state in the form of little bubbles. And so now you've just generated these little bubbles in your resin, and you got little bubbles running around, and they never do anything good. I mean, usually they tend to be attracted to and get trapped at the exact features you're trying to create. And so now you just wiped yourself out. And so we've tried so many different things to avoid generating those little bubbles, and none of them were entirely successful, or even maybe largely successful. And moreover, depending upon the time of year and atmospheric conditions, the generation of those little bubbles varies. So there was one time of the year where it was just always, oh no, our yield's just going to go way down because we're going to get more bubbles. And so kind of as a measure of desperation, because we didn't have anywhere else to go, a few years ago I said, well, let's just print in vacuum. Let's just completely degas the resin so that there is no gas to come out and cause this bubble problem. And so over a period of a couple of years, we got together some funding, and we designed this monstrosity of a 3D printer with a vacuum system attached, and it is a monstrosity. I mean, it's just, but it's a beautiful monstrosity, and so now actually we can 3D print and vacuum, and so we've begun exploring kind of this space, and we're far enough into it that we have a pretty good handle on what's going on and how to mitigate various issues. And in fact, this 1600 valve design was printed in vacuum. And so at any rate, that's kind of the overview of the story, and we'll have tons of details in the paper that we hopefully send out here in the next couple of months.
Amazing. So I think I'm curious as to exactly what the scale and the scale of the bubbles are, and what the scale of the features are that you're printing at, that has caused you this much angst that you had to do something like this.
Yeah. I mean, I think that the problem is the bubbles are near the scale or larger than the scale of the features. And basically as they form, they tend to stick to surfaces. Our 3D printing occurs at the surface. And so and the bubbles tend to stick to features. And so you end up with, a bubble in lieu of a feature, and the bubble's much larger. So you can imagine if you're trying to print 1600 valves, and you have a bubble that's about the size of 10 of those, and you can get a few of those, and you're connecting them all together. And instead of having all of them but two work, you have much less.
Yeah. So the size of the bubbles varies widely. I mean, they can be down around 20, 30 microns when squished into a single 10 micron layer, that they could be hundreds of microns. We've developed, and again, not published yet, but we've developed various types of bubble traps because they like to get caught on edges and corners. So we've developed bubble traps that are pretty effective at capturing bubbles if we locate those traps near features we care about. So we have some different tools that we have developed to deal with this, and the vacuum is one of those tools. But it turns out if you take the oxygen out, and the oxygen's an inhibitor, you cause yourselves all kinds of other problems. So we have
Such
solutions for that
as.
as well. And
Oh, good.
oh, well,
We will
yeah,
we will await
spontaneous
all of that.
polymerization. I mean, it's just, yeah, yeah. So
Yeah.
we've solved all of that, all of that now. We can get that to work out really well. I mean, as evidenced by the chip I was showing there. But maybe we should also say that so 3D printing in vacuum has been one of our kind of offshoot 3D printer development directions. But we have another direction, which is multi-resolution, which is where we use two optical engines to print a device. And so those two optical engines are in an XY stage, and so we can bring them to bear as needed within different regions of the entire 3D print. And so the lower resolution optical engine projects 15 micron pixels. And so the idea is you generate the bulk of your device at that lower resolution, which is still really high compared to what the commercial offerings are. And then we have this other optical engine that projects 0.75 micron pixels, so sub-micron pixels. And then with that, you basically create super high resolution structures only where you need them, and they're fully embedded in the rest of the print. And so we have then multi-resolution in X and Y because we have the two different projected pixel sizes, and then we also have multi-resolution in Z because we put two different optical absorbers in the resin, and we shape the emission spectrum of the two different LEDs that we use, a 365 and a 405 nanometer LED. And we tune everything just right with those two absorbers so that the 365 nanometer light sees 10 times the absorption of the 405 nanometer light. And therefore we have multi-resolution in Z. So with the 405 nanometer light, with the 15 micron pixels, we'll print 15 micron layers. With the 0.75 micron pixels at 365 nanometers, we'll print at 1.5 micron layers. And with that, we have just gotten some stunning results where we can embed these super high resolution regions. One example, Adams has a student who is really moving forward on it, is to embed very high surface area structures, high resolution, inside of channels. And so now you can think about 3D printing a chromatography column just directly. And that's looking very promising. And then another thing that we've done is created a little tiny mixer. I mean, in microfluidics, mixing is always so problematic because you're at low Reynolds numbers, you have laminar flow. It's mostly diffusion unless you try to induce some vorticity into the flow, which is just generally needs long channels and different structures in the channels. Well, so we have a different way of approaching that whole problem, and we have created this little tiny mixer that is maybe 500 microns long and maybe, I don't know, 300 microns wide and maybe, I don't know, 300 or 400 microns tall. And within that super, super small volume, we can do a complete, beautiful mixing of two flows very fast and very tiny volume. And the key to that is this super high resolution 3D printing ability, because what we'll do is we'll take each of the two streams, and if you just bring them together, you just get diffusion across the interface. So what we do is we split them into 6 different streams, make them really narrow, interleave them together, and so now you've got these streams that are maybe 8 to 10 microns wide, flowing side by side, and it just doesn't take very much time to diffuse across 8 or 10 microns. And so then we route that into this very narrow channel that itself is maybe 10 microns wide, and we serpentine it a little bit, in a few hundred microns. And then once you come out the other end, the fluid is just completely mixed. I mean, it's just beautiful. And so this is all done in a super tiny volume.
Wow. And it sounds like the scale of that mixer would be no more than maybe 1,000 microns long between the initial introduction and the serpentine and output.
Yeah, less than that, maybe 600 microns, something like that. Yeah.
And with that, you can stack a whole bunch of those in an individual 3D print. And again, that's one of the powerful things about this. If you want to do this at scale,
Yeah.
you could make dozens of them in a single 3D print.
Yeah. Yeah. So this multi-resolution, I think, is going to be an important innovation, and again, we'd love to see it in the hands of everyone.
What is the footprint of the 3D printer, the multi-resolution 3D printer?
So that one, it's maybe, I don't know, 3 feet by 3 feet by maybe 4 or 5 feet tall, something like that.
2 meters cubed, 1.5 meters
Yeah.
cubed.
Yeah, there we go.
There we go. We'll give it to you metric, right?
Yeah. And this is actually our second iteration. We call this our MR 1.1, multi-resolution 1.1. And the first one, the MR1, our first version of this, we did in 2019. Never published anything on it. And what we found is that the height of the thing, we used an aluminum strut, and the temperature excursions in our lab over the course of a day were enough to throw us out of focus. And so it just made it a bear to try to get results over any period of time. You could get one-offs, but it was just very difficult to keep it all in focus calibration. And so this MR 1.1, we've replaced the aluminum strut with a welded Invar structure, so it's much more thermally stable. And then we've also put these Keyence confocal distance sensors on both of the lens barrels of the optical engine, so that we can measure in real time what our actual distances are and compensate for any residual thermal drift. And that seems to work quite well.
So it sounds like the tech that you had to this new tech required another round of iterations of issues that you never would have imagined. When you mentioned temperature control, I was like, yes, you would have a hell of a time trying to make sure that you're in focus at at 3/4 of a micron, that you would be out of focus right away.
Yeah, these are really problems that you only run into when you really start pushing the edges. And, if you're making 200 micron features, it doesn't matter. But if you're trying to make, 3/4 micron pixels and getting the appropriate Z resolution for that, yeah, focus matters a lot. And so, yeah, temperature control, appropriate design of the materials for building the 3D printer, all of a sudden that stuff starts to matter a lot.
And even on our mainstream HR 3.3 series printers, which we have two that we've built, we use Invar in strategic places on those just to reduce the thermal sensitivity of the prints.
Amazing. So now that you've got these two projects, is there anything that you envision that's coming down the pipeline that you would love to share with us, or at least give us a bit of a snippet so we can wait for those papers to come out?
I don't know. Great question. I'm trying to be careful because there's some IP associated with some of them, so I do have to, be measured in what we're doing. But we're doing a lot taking advantage of this ability to make a combination of different sizes of 3D prints using this multi-resolution printer, and then again the ability to create many valves that are functional. We are looking at things like improving the ability to carry out chemical separations. And these are simple things like, I have a complex mixture that has, let's say it's blood or something like that. And we're looking for molecules. And in our case, we've studied molecules related to risk of a preterm birth, or we're looking at viral RNA from a mosquito-borne infection. And we've got this complex sample, and we want to just look at one molecule, one type of molecule, one class of molecule within that. And so to do that, we need the ability to control fluid flow. We need the ability to pattern surfaces with high resolution and attach specific molecules to those surfaces. And all of that really becomes enabled with both the HR 3.3 printers, the MR1, and then I haven't yet figured out what we're going to do with the vacuum one, but I'm sure we'll have some,
Well,
we once the workflow becomes, once he lets my chemistry students use that, if ever, I'm sure we'll be putting it to good use, because there's always things that you never knew you needed that 3D printer until somebody built it and you can make things. But from my lab, some of the advances are going to be this automation of simple wet lab processes to improve the detection of molecules related to disease. And that uses a combination of the different 3D printers and then some other things that we do in post-processing of devices to make it so we can carry out those analyses.
yeah, there's just so many things going on. I mean, all the way from one thing I've wanted from the very early days, 2015, 2016, is to be able to simulate the photopolymerization process on a layer by layer basis to be able to predict what structures you're going to get as a function of how you tweak various operating parameters. And so for fun, for me, just to get away from administrative stuff I don't like so well, the last year I've ended up teaching myself the finite element method, and found a paper that I really like from a group at Georgia Tech, and implemented a solution of a set of 4 coupled partial differential equations with the finite element method to simulate layer by layer what happens in the photopolymerization process. And so that's being very interesting. It's hamstrung a little bit by the fact that I don't have as much time as I would like to work on it, but it's at the point where we're getting relatively close to where we can open source that as a tool. And so that's one thing going on, and then that gets combined with some fundamental studies we're doing about the relationship between resolution and the irradiance with which you hit the resin. And we're finding some very interesting effects there where we can get resolution enhancements and single pixel channels. And so I've got a PhD student working on that, and hopefully she'll have a paper out sometime this year on that. And then we have some other, just weird phenomena we've observed over the years, and got some undergraduate students trying to figure that out. And then there's some really nice work out of Mehmet Toner's group at MIT, and also followed up some with Albert Folk at University of Washington on fluidic logic, fluidic transistors. And the point there is not that, fluidics is going to compete with electronics for doing computations. The point is rather that when you create, a chip that does a particular assay, it'd be really nice to embed the operational sequencing of that chip into the chip itself, so that in the end, all you have to do is take this little chip, have a completely untrained person put some sample into the chip, pipette on a couple of reagents, and then just hook it up to a vacuum source or a pressure source. And then the chip itself generates a clock, and then goes through the entire sequence required to do a complete biomedical assay. And so that's really the point of developing fluidic logic. And so to go in that direction, then you need nonlinear fluidic structures to do the transistor-like operations that you need for the fluidic logic. And because we can print with such high resolution and do crazy things, I've got a number of students who are working on different paths towards realizing these fluidic logic types of ideas with 3D printed structures. So maybe that'll fail, but we'll see what happens. So far, it's looking pretty interesting.
That sounds a lot like the ELISA chip. That's quite a bit larger than the chip that you're probably trying to develop, but it seems to sort of fit that logic set, I guess.
Yeah, right. Yeah, out of David Junker's group there at
Yeah.
McGill. Yeah, sure. Yeah, and he's using the burst valve approach, which is a
Yeah.
really nice way to go about things, and I think has just tremendous potential. But yeah, so this is another avenue towards something kind of akin to that, where the entire operation of the chip is embedded in the chip structure itself.
Well, we have come to an end of our conversation. It was extremely enlightening. As always, I didn't expect anything other than that. Thank you again, Greg and Adam, for taking time out and speaking to us and sharing your experiences to date, and then and giving us some highlights into exactly what is coming around the corner as well.
And thanks so much for hosting us. It's been a delight
Yes,
chatting with you.
yes, thank you. It really has been. We really appreciate you and all that you're doing in the 3D printing and microfluidic space, and just love that you're making things available to people so they can pursue their dreams in terms of applications.
Thank you very much. And that ends this episode, and we will see you next time around. Bye for now.